Hi Satish. Sorry for the delay. There were some technical issues due to which I could not join earlier. Um, so I guess since only you are in the session right now, we can wait for 5 to 10 more minutes so that a few others can join the session. So I'll be muting myself for next 5 10 minutes so that some few more people can join the session in person and like participate in the discussions. So we'll get started in like 10 minutes, let's say. Okay, so I guess no one has joined the session in person yet. So I guess and nonetheless we can get started for the for the YouTube audience. So like just to reintroduce myself for the YouTube audience, whoever's watching on YouTube. Hello everyone, I'm Lakshya Saggi. I'm the problem solving TA for the NPTEL Games and Information course for the Monday 6 to 8 p.m. sessions. And this will be our fourth session. And in this session, we'll be discussing problems related to mixed strategies in zero sum games. So basically, whatever was discussed in this week's lectures, like the von Neumann's theorem, Min-max theorem, and yeah, stuff like that. And once again, like all times, I'll be assuming that while discussing the problems that everyone has gone through the lecture videos posted on the NPTEL course, and we'll strictly be focusing on the problem solving part, which will help you for the weekly quizzes. I guess we can get started in that case. I'll just share my screen and start discussing the problems. So I'll just share my screen now. Also, sorry for the delay in the session today. There were some technical issues due to which uh, I was not able to connect to the meeting, and we have started half an hour late because of that. Okay, so I hope my screen is visible to everyone. So uh, I guess now we can get started. So this, as I said, this is the week 4 of our session, and yeah, we'll be talking about mixed strategy. So I prepared a bunch of problems for this for discussions for today's session. So one, first of all, like a basic convention, which we'll be assuming like it's a very standard convention, which is news that in a zero sum game, we'll be assuming that the column player is trying to maximize his payoff, and essentially the row player is trying to minimize his payoff. That's why we write the min max expression for the row player and max min expression for the column player. So that kind of thing. And in a non zero sum game, both players are maximizing their payoffs. So these are the conventions which we'll be assuming. And so, like all times, we'll get started with a bit of an easier problem. So the first problem is somewhat of an easier problem, and it's just a problem lec based directly on the lectures only. So the problem states that a consequence of von Neumann's min-max theorem is that a pure saddle point strategy exists for a two-player zero-sum game. So is this true or false? So von Neumann's min-max theorem actually discusses about mixed strategies, that there always exists a mixed saddle point strategy, not a pure saddle point strategy. And we have discussed in previous session also, and like it has been already discussed in like lectures also, like the rock paper scissors example, that there need not always exist a pure saddle point strategy anyways. So anyways, the statement is false that a pure saddle point strategy exists for a two-player zero-sum game. Like it is possible that it does not exist, but what von Neumann showed is that always a mixed saddle point strategy will exist. And this is an important part. So actually, this statement is false. That a pure saddle point strategies exist as uh, pure saddle point strategies need not always exist. And just to quote um, von Neumann theorem also talks about like existence of strategies, but it talks about existence of mixed strategy. Theorem talks about existence of mixed saddle point strategies. Okay, then. So, I guess this was just a warm up. And then we can get to the second question now. So, second question is a bit of a numerical based question. We'll be focusing more on numerical based questions today because yeah, mixed strategies, the question related to mixed strategies tend to be a bit numerical, anyways. So, second question states that let the matrix A, which is given to us, let the matrix A be the payoff matrix for a two-player zero-sum game. Suppose we compute the value of Vm over line over Vm bar A by formulating it as an LP problem. Then which of the following points of the form T comma Y lies in the feasible region of the LP? So just to just so that everyone is on the same page here, like I hope everyone is able to understand the question. So first of all, we are given this matrix A for a two-player zero-sum game. And now what we want to compute is this value, Vm bar of A. Essentially uh, like the saddle point value for the row player, the min-max value. You may remember that V underline M was used to refer to the max min value, and V overline, or basically V bar M, was used to represent the min max value. So this was already discussed in the lectures, this notation. And uh, so to calculate this value in case of mixed strategies, we formulate it as an LP problem, as was discussed in the lectures. And then now we need to find out which of the following points of the form T comma Y lies in the feasible region of the LP. So it might be confusing, like what's T comma Y. Again, this notation was also discussed in the lectures. Maybe I have also like uh, just so that everyone, so like for a quick revision for everyone, I have already like taken a screenshot of these notations which were discussed in the lectures, and I'll just maybe put these also in, like after convention and before the questions start. So yeah, LP for calculating. So consider this as like a quick revision note, maybe like if we want to if one wants to calculate a VM of A, then this is the LP, which one, which we are talking about. And similarly, if one instead wants to talk about calculating V underline M instead of A, like this is the min max value, right? We have to do like minimize over T and stuff like that. And if one wants to calculate V underline, okay, then this is the LP which was discussed in the lecture. And by LP, I mean the linear program. I think this should be obvious, but yeah. So this is nothing fancy. This is just taken from the lectures directly. Like this is the LP for calculating VM of A is just you have to minimize over T and Y, the value T, and the constraints given, and the constraints will be A transpose Y minus 1 is the all ones vector times T is less than equal to 0. Similarly, 1 transpose Y is equal to 1 and Y is greater than equal to 0. And similarly, if one wants to calculate so this was also discussed in the lectures that this LP, the LP for calculating V underline M, is nothing but just the dual of this primal LP. So this is the primal and this is the dual LP, and this dual LP is used to calculate V underline M of A. But right now the question asks us about this. Uh, Suppose we compute the value of V bar M of A by formulating it as an LP problem, then which of the following points of the form T comma Y lie in the feasible region? So here we see that this is the LP which we'll use to calculate actually this value. And now someone asks us what will be the values of the what will be the points T comma Y Like what the question asks us is we want the question gives us some of the points. Like the question gives us some points like uh, this point, and this point, and this point, these 4 points. And it just asks, it does not ask about any optimal value or anything. The question asks which of the following point lies in the feasible region of the LP. And what do we mean by feasible region in an LP? So feasible region is just this set of constraints being satisfied. So note that in a linear program, we have to optimize some objective function, right? We have to minimize the value of t and subject to some of the constraints which we are given, like A transpose Y minus 1 times t is less than equal to 0. Similarly, 1 transpose Y is 1 and Y is greater than equal to 0. So we have to minimize this objective function constraint to these constraints which are given to us. Such, and now, and note that here t will just be a singular value and like y will consist of like two values. Like y will be a 2-dimensional vector and t will be just a scalar value. And why is that? Because in this question, it's just a 2 cross 2 matrix given to us. So maybe for ease, I'll just copy this here also. Yeah, maybe I'll just copy everything. Yeah, for ease of understanding of everyone. Everything on a new page. Yeah, yeah. No, I guess it's a bit better. So now these are the constraints which we need to see whether they are feasible or not. We don't need to worry about this objective function value, the value like this, minimizing the objective. What we are really worried about is the question asks us about the feasible region of the LP. And feasible region is the region in which these constraints which are given to us are satisfied. So what we just do is we see these points and we just check whether these points satisfy these constraints. And note that we are given the values of the form t comma y, but like these are 3 dimensions, but t and y are just two variables. But note that it's easy to see that t will just be a scalar, so t is the first value of these uh, 3-dimensional vectors, and y is a 2D vector, so y is like. So here in this option, what it essentially means is that we are checking whether t equal to 3.5 and y equal to zero point 0.7 comma zero point 0.3 is feasible or not. Similarly, in B option, we are checking if t equal to 1 and y equal to 0.5 comma 0.5 is feasible or not. Similarly, we are checking C option, D option, and like if none of these are feasible, then none of these. So and we just need to check these constraints. So maybe we can go option by option and see which of the which of these constraints are actually feasible. So let's try option A now. In option A, we are given that t equals to 3.5 and y equal to zero point 0.7 comma zero point 0.3. Okay, so to check if this constraint is feasible, what we need to do is we need to just put in these values. This is a very simple problem. We just really need to put in these values in these constraints. So let's check the first set of constraints. The first set of constraints is that A transpose Y minus 1 times T is less than equal to 0. So maybe we should just first calculate A transpose Y. So we should just check what this A transpose Y value comes out to be. Because 1 times T, 1 is just a vector with all ones, and T is just 3.5. So this will just become a vector with all values as 3.5, 1 times t. So we can worry about it later, but for now we should just worry about maybe calculating this value A transpose Y. And how do we calculate this? So again, it's not. too hard. So maybe I should just insert something. Yeah. Okay. I guess this is good enough. So what we really have here is that we are given the matrix A equal to this. The matrix A is essentially 2074, right? And so what will be the matrix A transpose? It will just be 2 and 4 will remain the same, but 0 and 7 will change. So the matrix A transpose. So to calculate A transpose Y, what we really need is first find out the matrix A transpose, right? So 2, 4, and this entry will become 7 now. So 2, 4, and 7, and a 0. Okay. So Manas, I guess Manas has joined the session. So hello Manas. So we have already started with the discussions, but this is just a second question which we are discussing just as a recap for you. The first question was just a straightforward question about whether pure saddle point strategies exist or not. And now like we are talking about the second question and second question what we the second question asks us to formulate the given zero sum game as an HB problem and then find out whether the given points are actually in the feasible region of the LP or not. So the linear program which we want to like which we want check which we want to check for feasibility is nothing but the linear program which was discussed in the lectures. Like if we want to find out the value of v bar m of a, what we just really want is to use this kind of linear program formulation. This was already discussed in the lecture. V bar m of a is nothing but that min max overall like mixed strategies, and it comes out to be equal to this linear program. Like this is nothing new. This is just straight from the lectures. And now what we want to check is like for all these options A, B, C, D, we want to check whether these options satisfy this linear program or not. Like for example, so we are not really concerned with this objective function's optimal value. We really don't want to optimize the objective function. What we just want is to check the feasibility. And what do we mean by feasibility? By feasibility, we just mean we want to check whether these constraints are followed by these points or not. These set of constraints are followed or not. So the first set of constraints just says that A transpose Y should be less than equal to uh, 1 times T, where one is this one is just a vector of all ones. And similarly, 1 transpose Y is 1. This just means that sum over all values of Y should be equal to 1. And similarly, all values of Y should be non-negative, right? So the first constraint really just means that each so A transpose Y will be a vector like A is a matrix, A transpose is a matrix, and then multiplying it by the Y will just give me a vector. And now what I really want to check is whether all the entries of that vector are less than equal to T or not. If they are, then this constraint is satisfied. Similarly, we'll be checking with second constraint and the third constraints also. So to find out whether all the entries of the matrix A transpose Y are indeed less than equal to T, we first actually need to calculate the value A transpose Y, right? So we'll do it option by option. So first option is this, the T comma Y are given to us are 3.5, comma zero point 0.7, comma zero point 0.3. Note that T is just a scalar value. So like T just refers to this point 3.5 and Y refers to these last two dimensions 0 0.7, comma 0 0.3. Similarly, this will be in all options like in B option T equals 1 and Y is 0.5, comma zero point 0.5 and so on. So maybe just we'll stick to option A for now. So in option A, we are given that T equals 3.5 and Y equals 0 0.7, comma zero point 0.3. And now we really need to just calculate A transpose Y. Or maybe I should first write down what's the value actually A transpose Y. What is maybe we should just first write down what actually is A transpose. Here, A transpose is equal to. So this is the matrix A transpose actually. And how did I obtain this matrix? I was given the matrix A. Its first is this into it was just 2074. And how do we take the transpose of a matrix? We just replace the rows by columns and columns by rows. So 2 comma 7 will be the first row, 0 comma 4 will be the second row. And this is what we get. 2 comma 7 is the first row and 0 comma 4 is the second row. So what will be the value of A transpose Y for us? So A transpose Y is equal to. So I hope everyone remembers matrix multiplication. So this is the matrix A transpose and Y is this vector 0 0.7 comma 0 0.3. So basically think of this as Y being a column vector whose first entry is 0 0.7 and second entry is 0 0.3. So Manas, would you like to point out what will be the value of A transpose Y? Like A transpose is this matrix and Y is this vector. Like it's fine even if there is a mistake or anything. I would just like you to try it out. Okay, maybe while Manas is trying it out, I'll maybe just discuss this. Like this is kind of a uh, oral calculation, really, but yeah, maybe I'll just do it for everyone here. So note that y is a vector which has the entry 0 0.7 comma 0 0.3. So how do we define this matrix A transpose Y? So like A transpose is given to us, and now we want to multiply it by Y. What we need to do is just uh, so think of Y as being a column vector here, right? So what is really the value A transpose Y equal to? It will be a two-dimensional vector whose first entry will be equal to 2 times 0 0.7 plus 0 0.3 times 7. So it will be something like 2 times. So this entry will get the first column will get multiplied with the first row of this vector. Second column will get multiplied with the second row. Like this is standard matrix multiplication I'm doing. Nothing new. So also Manas, if you have doubts at any point of time, feel free to stop me and like ask me in chat and I'll try to answer your doubt as best as possible. So feel free to ask doubts in chat. So we are talking about the first entry of the vector. So the first entry of the vector will be 2 times 0 0.7 plus 7 times 0 0.3. And what will be the second entry? The second entry will be 0 times 0 0.7 plus 4 times 0 0.3. And what this is actually equal to. So this is the value of A transpose Y. So note that 0 point, I'm doing it a bit orally because I think these calculations are not that hard. So 2 into 0 0.7 will be 1.4 and 7 times 0 0.3 will be 2.1. So 1.4 plus 2.1 is equals to 3.5. So first entry becomes equal to 3.5 and second entry will be 0 times 0 0.7 will be 0 and 4 times 0 0.3 will be 1.2. So this will be 3.5 comma 1.2. So note that A transpose Y has entries 3.5 and 1.2. And like both of these values are less than equal to 3.5, which was the value of T. So this is actually less than equal to, maybe I should just insert an equation here. Okay, do I write this? Is it like, yeah. So this is indeed less than equal to 1 times t. And how do I write this one? Maybe x. Okay. Okay, maybe I'll just write it as 1 times 3.5. No, this doesn't look nice. I'll just write like this. So this one in bold denotes actually the one vector, 1 times t. And why is this the case? Yeah. And why is this the case? Like, why is this less than equal to 1 times t? Because t was actually 3.5 in this. Maybe I'll just bold this so that it's everyone to see. It's easy for everyone to see. So we just calculate the value of A transpose Y. So at least this constraint is satisfied that A transpose Y is less than equal to 1 times t. This constraint is actually satisfied. Now we need to check for the second constraint, whether the second constraint is also satisfied by these values. The second constraint just says that the summation of the y values, so note that this constraint is just equal into summation of the y values should be equal to 1. So the all the entries of the y vector y should sum up to 1. And all entries should be non-zero. So these two constraints just state that all the y entries should be non-negative and should sum up to 1. And here you can see that like both the entries are non-negative and both are actually summing up to 1 because 0.7 plus 0.3 is equal to 1. So actually these constraints are also satisfied. So also uh, I'm writing this 1 in bold because 1 in bold denotes the vector of all ones. Maybe I'll just write it in the notation also. Notation 1 denotes the vector, the column vector containing all ones. So this is what this denotes. So yeah. So now this 1 transpose y will be equal to 0.7 plus 0.3 here, which is 1. And y is also greater than equal to 0 because each of the entries 0.7 and 0.3 are greater than equal to 0. So something like this. Yeah. So I hope this makes a bit of sense. So option A is feasible. Hence option A is feasible because all of these constraints are satisfied. Now let's come to option B then. So maybe I'll just copy the syntax here and maybe just see what values are changing. So note that in option B, we have t equals to 1 and y1 and y equal to 0.5, 0.5. So we have t equals to 1 and y equal to 0.5, 0.5. So what will be the value of A transpose Y? It will be 2 times 0.5 plus 7 times 0.5. And the second entry will be 0 times 0.5 and 4 times 0.5. And this will be equal to, so 2 times 0.5 is 1 plus 7 times 3.5. So 7.7 times 0.5 will be 3.5. So this will be 3.5 plus 1, which will be 4.5. And the second entry will be 0 plus 4 into zero point 0.5, which will be 2. So this will be 4.5 comma 2. But note that t was given to us as 1 here. T is 1, but you can see that these entries 4.5 and 2 both are actually greater than t. So actually this constraint is not satisfied. Since 4.5 is greater than t, hence the first constraint is not satisfied. So since we have found at least one constraint which is not satisfied, then this just means that yeah, so we don't need to check for other constraints because we have found already one constraint which is infeasible. So this solution will be infeasible. So option A is feasible, but option B is not feasible. I just underline these answers. And now coming to option C, what do we have in option C here now? Let's see. So option C says T is 7 and these two values are 0.6 and 0.5. So in the C option, maybe I'll just copy these. So we are given that T is 7 and these two values are Y is 0.6 comma 0.5. So now, okay, maybe we should just remove this, all of these. So now in this value T and Y, what I'm claiming is I don't even need to calculate the value of A transpose Y. Like even without calculating. Okay, so Manas is asking in the chart that we have to check what we are doing is basically checking every constraint. Is there any other smart method? So actually, Manas, I don't think there is any other method by which you can check this. But note that it's not very difficult to check all of these constraints. I'm just doing this calculation explicitly for everyone to see. So that's why it's taking a bit of time. But note that you can just do this all of these calculations even orally also. Like none of these calculate like it's just multiplication of a 2 into 2 matrix with like a vector of just two entries. So it's not like too difficult to do anyways. So you have to just take these set of constraints and yeah, this is how we will have to go about it. And like what I believe is it's not too difficult. It's like quite straightforward also. So like in option C, the infeasibility is actually very obvious. Like you don't even need to check the A transpose Y, the value of A transpose Y. I claim that you don't even need to check the value of A transpose Y. You can just see from here directly that this is infeasible. And Manas, can you point out, would you like to point out why is this set of values infeasible? Like I can directly say that option C is infeasible, but what's the reason? Would you like to point out the reason? Like in chart. Okay, so Manas is typing something in the chat. Yeah, it is outside the constraint, that's right. But I was explicitly asking which constraint does it not satisfy? But never mind, like maybe I just straightforward say. So note that one of the constraints said that sum of the all the y values should be equal to 1. But here you can really see that the sum of the y values is actually equal to 1.1 and not actually equal to 1. So yeah. maybe I'll just copy this. So since 1 transpose y here is nothing but 0.6 plus 0.5, which is 1.1, which is greater than 1. Hence option C is infeasible. So now let's come to option D maybe. Okay, I'm just doing this for all the options because like all the options show actually different set of constraints not being satisfied. So option B showed this constraint being infeasible. Option C was infeasible because of this constraint. And option D will be infeasible because of this constraint. All the y values should be non-negative, but here you can really see that one of the y values here is negative, like minus zero point 0.1. So yeah, what are the D and y values? 11 and yeah. So here what we have is D is equal to 11 and y is 1.1 comma minus 0.1. So here this is also you can directly say that it is infeasible because since y cannot contain negative values, hence option D is infeasible. So I hope this makes sense. So options B, C, D are infeasible. Only A is feasible. So we had to point out the points which lie in the feasible region. So only A lies in the feasible region. So in finally, the final answer will be hence option A is correct. This is the final answer. Uh, and yeah, I think there is a similar question in this week's quiz also. So for that also you'll have to do it. Yes. So yeah, Manas, you're actually correct. Like you have to know the axioms and yeah, just check the feasibility using those. So yeah. So now we move on to the next question then. The third question is again a very straightforward question. It's just a revision of what has been discussed in the lectures. So suppose an LP problem attains an optimal value, then the optimal value of the dual LP also exists and is the same value. Is this statement true or false? So would you like to answer this question, Manas? Is this true or false? The the problem 3. Okay, so Magnus is typing something in the chat. So I think Manas, you're asking something about the second question here. Okay, so Manas is saying that. So Manas, are you talking about the problem three here or problem two? Because I think so in problem two, I don't think you need to really check anything about the duals. Like problem two here is just talking about this V bar M of A, and for this you just need to check the primal LP. If one is talking about the if one instead is talking about, let's say, the V underscore M, if one instead is talking about calculating V underscore M of A, then you need to check the dual, and the LP for calculating the dual is this. Like this was also discussed in the lectures anyways. So this is not something which is new. So yeah, this snippet is again from the lectures for calculating the dual L for calculating using dual LP, and this is the primal LP. And oh, okay. So you're asking about some other question of the assignment. Okay, never mind. Like, I don't think I can directly answer the assignment questions for you because, like, they are kind of the quiz. I can answer these questions next week, maybe when you are done with the submissions. For now, maybe I can only answer like questions which are not in the assignment. Okay, so Manas is typing something again in the chat. Okay, sure. So, so Manas, for third question, what do you think? Is this statement true or false? Like, so if uh, does the optimal value of dual LP equal to the is the optimal value of the dual LP equal to the value of the primal LP? Maybe you would get your answer while answering this question. Yeah. So that's a good job, Manas. Yes, actually, this was also straight away discussed in the lecture. This was directly discussed in the lectures that uh, that uh, the LP attains an optimal value, and optimal value of the dual LP also exists and is equal to the same value. This was like this is just a straightforward revision from the lectures. Yeah, so nothing new here. Okay. Then I guess we can move on to the fourth question. So fourth question says that again we are given a payoff matrix for the two-player game, and what is the value, and now we need to find out what's the value of the game up to two decimal places. So we are given this payoff matrix for the game, and we need to find out the value of the game. And what do we mean by finding out the value of the game? We kind of need to find out the maybe like the deterministic, the pure strategy, pure straddle points, or maybe the fixed saddle points, whatever exists for this game. So we'll just try to like find out the mixed strategy saddle point for this game because like that's what the value of the game corresponds to, right? So maybe I'll do this question. Uh, like maybe we can try to do this question. Like these kinds of questions have also been discussed in the lectures, but just for additional practice. So this is the payoff matrix given to us for this, and now we need to find out what's the value of the game up to two decimal places. So maybe let's first look at the row player. Okay, so for the row player, we can assign some like we can assign, let's say I assign the probability y1 uh, to the choice one, which is like row one is just this choice t, and this is, let's say, row two. So this is row two and this is row one. So the value y1 corresponds to like probability of choosing this row one, and y2 corresponds to probability of choosing row two. So maybe if I plot this thing, note that if the column player plays column one, then the payoff for the column player will be something like minus y1 minus 3y2. So maybe I should plot this thing. So I have this like online plotter kind of thing. This is Desmos like where you can easily plot. So I had this open. So maybe I'll just plot this kind of thing. So what we had was suppose if the first uh, so for a y1 for a given y1 comma y2 vector of the row player, the first column corresponds to minus y1 minus 3y2, right? So this is actually the so what essentially means is something like if y1 is actually equal to 0, if y1 is actually equal to 0, then the payoff will be somewhat of a minus 3 for the first column. Like for the first column, the payoff will be equal to minus 3 if y1 equals 0. And if y1 equals 1, then the payoff will be kind of minus 1, right? So how should I write this up? Yeah. Okay, maybe I should not write it like this because it might get a bit confusing. So yeah. So note that what we want here is like if y1 is 0, like what will the line corresponding to the first column? So what we are saying is if y1 is 0, then the plot should go through the point uh, minus 3. So what I'm plotting here is on the x-axis I'll be having, maybe I should label my axis. So x-axis is just my y1, let's say, and the y-axis is just my, maybe let's say, value of the objective, right? So if my y1 was 0, then the value was minus 3. So it should go from this point minus 3 comma 0 to the point when y1 becomes 1. When I'm choosing this strategy, it should go on to become minus 3. Okay, it should go on to become minus 1 when y1 equals to 1. So when y1 actually becomes equal to 1, it should go to minus 1. So y1 is just a straight line. Like, so this is just a straight line which goes from like minus 3 to minus 1. So this will be the kind of straight line which we are talking about. So maybe write it in, we'll write it here directly. So what we want is we want the point such that it goes through minus 3 comma 0, and uh, it goes through 0 comma minus 3 because x-axis is y1. So it goes to 0 comma minus 3 and it goes through 1 comma minus 1. So maybe I should write it here. So yeah, it's you y1 comma y2 to be the distribution for the row player. Probability distribution for the row player. Then the payoff for the column player on playing. So what will be the payoff for the column player on playing column 1? On playing column 1, the payoff will be equal to minus y1 minus 3y2, right? Because minus y1 times minus 3y2, and while playing column 2, the payoff will be equal to nothing but minus 4y1 and plus 3y2. So these will be the payoff for column 1 entries and the column 2 entries. And also note that we know that y1 plus y2 is actually equal to 1, right? So yeah. So what this essentially means is something like so this is the value. So this is the payoff value. So column 1 is this payoff. Like column 1 denotes the payoff on the column 1 when playing column 1. And this is equal to minus y1 minus 3y2. And note that y1, and note that I can replace y2 by 1 minus y1 because y1 plus y2 should be equal to 1. So this can be written as minus 3 times 1 minus y1. Right? So what I get is this value, the the payoff value. This is on my y-axis here. The value is on the y-axis. So this is essentially equal to just minus y1 minus 3 times 1 minus y1. And y1 is on the x-axis for me. So this is the plot I want. What I want is y equals to minus x minus 3 times 1 minus x. This is kind of what I want. So, so y equals minus x minus 3 times 1 minus x. This is the kind of plot I want, and I just wanted to uh, be restricted to just 0 to 1. Like it shows values for more than domains of more than 1 and less than 0 also, but we'll only consider the domain from 0 to 1s, right? So I hope this makes a bit of sense. Like, why are we doing this? Okay, so Manas has already written in the chat the steps. So that's good, Manas. So similar thing we'll try to do for the column 2 player now. So for the column 2, we have minus 4y1. So maybe I'll just write it here also. So this is just minus 4y1 minus 4y1 plus 3 times 1 minus y1. Yeah, this is now what I want to plot. So this is my y-axis, the payoff is on the y-axis, and it is nothing but equal to minus 4y1 plus 3 times 1 minus y1. So y just becomes x in this plot. So like, so what we are really doing is y equals to minus 4x plus 3 times 1 minus x. So this is the plot which we have, right? So now note that we are just interested in the domains where y1 goes from 0 to 1, right? And whatever y1 we choose, what the expression which we actually want is minimize over y1 and then a maximum over all the columns. So column player will try to choose the maximum entry of these. So note that, like, suppose when y1 was equal to 0, so there are two values available for us. Can choose something so that the final entry becomes this 3 or it becomes minus 3. So column player always wants to maximize. So column player will choose this thing. So what essentially we'll be choosing is at all points we'll be choosing the curve which lies on the upper side. So between these, so at this intersection point to this point 1, we'll be choosing this red curve because it is higher than the blue curve. And in this and the remaining range, we'll be choosing the blue curve because it is higher than the red curve. So this will be what the column player will choose. So this curve is what will be followed by column player. But now note that the row player actually wants to minimize this value. So what is the y1 at which this whole value gets minimized? It's this point, right? It's this minima point because before that everything is greater than this point, and after that also everything is greater. So this is the point at which it is actually minimized. So note that. And the y1 value here is equal to 0.6666, and the value of the game is minus 1.6666. Or like essentially this is nothing but like uh 2 by 3 comma something like minus 5 by 3. Yeah. So the value for the game achieved is equal to minus 5 by 3, and the probability distribution is 2 by 3 comma 1 by 3, right? So this, from plotting the above expressions, we get that the value of the game is actually equal to minus 5 by 3, and it is achieved at y1 equals to so what's the value of y1? It's 2 by 3, and the second value is 1 by 3. 2 by 3 and y2 equals 1 by 3, right? So note that this was what was required as the final answer. So we get this, and we also get the value that which is. But just for sanity check, since like you don't need to do this in exam while doing exam, but since we are here to learn, maybe what we can do is instead of trying to solve this problem using um, from the perspective of the row player, let's try to solve it from the perspective of the column player now, just for fun, so that we are able to understand the problem even better. So right now we chose the probability distribution for the row player, but now we'll do it for column player. So these kinds of things, maybe I'll copy and we'll just change everything to column player. So let me maybe just, yeah, maybe I'll just, let's have a new one because I want to save this plot because maybe we will be using this plot further. Yeah. And here what I'm doing is now, right now, so this is maybe just an alternate way in terms of column layer, right? So what we do is we'll assume that Z1 comma Z2 is the probability distribution for the column player, right? So we know the probability distribution for the column player. And now what we want is we want to see the payoffs for the row player on playing row 1 and row 2. So row player plays row 1 or it plays row 2. And let's see what the row player gets on playing row 1. So note that in column players, we get that the first column is Z1 and the second column is Z2, the probability. So if the row player plays row 1, he gets minus Z1 minus 4Z2. So the row player gets minus Z1 minus 4Z2, which is nothing but equal to minus Z1 minus 4 times 1 minus Z1, because Z1 plus Z2 should again be equal to 1. And now what does the row player get on playing row 2? It's minus 3Z2. It's minus 3Z1 plus 3Z2. So it's minus 3Z1 plus 3Z2. So it's minus 3Z1 plus 3Z2, which is again nothing but minus 3Z1 plus 3 times 1 minus Z1, right? And now maybe we'll just see, we'll just try to plot these expressions now and see whether the answer for the game matches for us. So here we'll have like the payoff will be again on the y-axis, the z1s are on the x-axis. So here again we'll have like, maybe on the y-axis we'll have the value of the game, and on x-axis we'll have the z1s. And now the expression for us is something like uh, y equals to minus x minus 4 times 1 minus x. The first expression is y equals minus x minus 4 times 1 minus x. So this is the expression which we get. Similarly, the second expression which we get is something like this. So the second expression which we get is y equals. Note that you don't really need to use this Desmos tool or anything to calculate because this is quite a simple thing. But I'm just using this because it's easier to show it like when I'm sharing my screen, like because I can't share my what I'm doing on copy and print, so it's easier for me to show it using this. But otherwise, like obviously these are very simple calculations, so you can do these like yourselves also. It doesn't really matter. So maybe I'll just what's the range I should put for a better view of what's happening now. -44 and maybe x goes from -0.5 to 1. Yeah, I hope this provides a much better view for what's happening. Yeah. So these are the two plots which we had. And again, now for the column player, what we want is uh, the row player wants to minimize and the column player. So here we are calculating the value of max of min. So what will happen is for anything which column player chooses, the row player will want to minimize it. Maybe again, I should just do it -4.5. Yeah, so that it's better. So row player will always want to minimize whatever column player wants to do. So if column player chooses something like, let's say Z1 equal to 0, row player has two choices to choose 3 or -4, and row player wants to minimize, so he'll choose -4. So always will be whatever choice column player makes, the curve which will be followed will be the lower curve. But the column player now wants to find the maximum out of all these values, and note that the maximum will be achieved at this point, like this is the highest point. And note that again you can see the value here is again -1.666, which is like -5, which is the value remains the same, but the probability, the Z1 chosen by the column player is something like this, 0.777778. So yeah, so again the value of, we again get that the value of the game is -5/3, and it is really achieved at Z1 equals to 0.7 bar, and it's I think nothing but equal to maybe uh 7/9, I guess. So it will be like 10x equals to 7.7, and so it will be 7/9. So Z1 is nothing but 7/9, and Z2 is nothing but 2/9. Yeah. So yeah, so since the question just asked us to find out the value of the game up to two decimal places, we really just need to find out this -5/3. And you did not need this alternate way, but I just did this so that we are a bit more clear on how to do stuff. Okay, then okay. So now if we are done with this fourth question, now let's maybe move on to the fifth question now. So fifth question is again similar to the kind of questions which have been discussed in the lectures also. And yeah, so here we are essentially so maybe I'll just duplicate this because I'll be again plotting using these terms. So in the fifth question, we are given basically a 2 cross 3 matrix. So there are three choices for the row player and two choices for the column player. And now we really want to find out what's the value of the game here. So note that again we are just asked about the value of the game. So in previous question we I tried to say like find out the probability distribution also, but maybe here we'll just focus on finding the values because we have already discussed on how to find out the probability distribution. Okay, so since we are more comfortable with like plotting things to really understand what's going on, so and plotting is usually easier in 2 dimensions, right? So we'll try to plot in the dimensions, in the smaller dimensions, like as was done in the lectures also. So note that here there are three rows. So if we try to formulate this problem in terms of rows, we'll have three variables, y1, y2, and y3, and then one constraint that their summation is equal to 1. So this formulating it in terms of probabilities of rows will be a bit difficult as it will involve more variables. But note that if you formulate the problem in terms of columns, then you'll just have two variables z1 and z2, where z1 plus z2 will be equal to 1. So it's easier to formulate the problem in terms of the column layer. And that's what we'll be doing because we want to always arrive at the answer as efficiently as possible, right? So here, since there are just two columns but three rows, will be since there are yeah, three rows and two columns in A, it's easier to find the value of the game in terms of or maybe by finding the probability distribution with respect to column player, because column player has just two columns, two strategies to choose from, and row player has three strategies to choose from. So again, maybe I'll just copy this whole thing and I'll just change the values which we obtain. And obviously we'll be needing to plot a lot of more things. So suppose Z1 comma Z2 is the probability distribution for the column player. So the first column is played with probability Z1, second is played with Z2. So then the payoff for the row player on playing row 1, so what will, if the row player plays row 1, the payoff will be 2 times Z1 plus 6 times Z2. It will be 2 times Z1 plus 6 times Z2, which will be nothing but equal to something like this. Right, 2 times Z1 plus, I just replace Z2 by 6 minus Z1. And similarly, if the row player plays the row 2, then it will be 5 times Z1 plus 5 times Z2. So row 2 will be just 5 times Z1 plus 5 times Z2. And note that actually this will just come out to be a constant because Z1 plus Z2 equals to 5, right? So this will actually be just equal to 5 because Z1 plus Z2 is 1. Row 3 is nothing but 7 times Z1 plus 4 times Z2. Okay. And this is nothing but if I put Z2 equal to 1 minus Z1, this will be nothing but 4 times 1 minus Z1, right? Yeah. So these are essentially the three values. Like these are the three choices for the row player, which the row player can make. So now again, we'll be trying to plot these things. So maybe again, I'll be using x-axis maybe from minus 0.5 to 1.5. And note that we are characterizing it in terms of Z1. So we'll be using this. We are plotting the value on the y-axis and we are using Z1 on the x-axis. And what are the possible values which we'll be taking? Maybe we can just see. So the first expression is nothing but 2Z1 plus 6 times 1 minus Z1. So this is so the equation which we just want to use is y equals to 2x plus 6 times 1 minus x, right? And similarly, the second expression will be just y equals 5. And the third expression will be nothing but y equals 7x plus 4 times 1 minus x. Yeah. So these are the three expressions which we really want. And Yeah, maybe I'll just I can maybe change the values of the y so that it's a bit it's a bit better. Yes. Okay, I hope this is better now. It's visually more appealing. So we are just concerned between the interval z1 goes from 0 to 1. So between these intervals, we are talking about the column player right now. So whatever column player chooses, so we need to find out the row player will try to minimize it. So what we are doing is, so we have these three curves and row player will always have three choices and row player will always want to minimize because we want to find out maximum over column player's choices and the minimum over row player's choices. So row player will always want to minimize. So the curve which will be of importance to us will be the one which is always lying on the lower part. So note that this so initially, as you can see, the green part is the lower part from 0 to like this point. And after that, the red takes over as the lowest point. And note that this blue part, the y equal to 5 part, never becomes actually the lowest point. So actually like this is somewhat redundant. The second row, or basically the second strategy is useless for the row player. So row player will always try to do something with the first strategy or the third strategy. And note that the column player wants to maximize over this curve. So the maximum value will be at this point. And note that this is the point which we'll be uh, using. So this is the point, and note that the value at this value obtained at this point is equal to this 4.857. So it's a fractional value which has been rounded up using decimal places to this value. So this is like the value for us, which is the value, and it is achieved at z1 equals to this. So this is the optimal value. So maybe I'll just write it as 4.86 maybe. So, so this is nothing but equal to 4.86, and maybe I'll just write that it is an approximate. And what Z1 is it achieved at? It's achieved at 0. Let's say 29 maybe. Again, it's approx. And but we really don't need to worry about the Z1 because the problem just has to find out the value of the game. And value of the game is this 4.86. Okay, so I hope it's easy for everyone to see. And also note that if one still wanted to, so find out. So we found out the probability distribution for the column player. But if one is interested in finding out the probability distribution for the row player, one might get confused as to how to obtain that. So one thing to clearly see from here, this was discussed in the lecture also, that the row player will never want to play this second strategy, the blue line, because it is always uh, above our important part. So maybe, so what one can do is just ignore this blue strategy. So just ignore this second row and just consider this 2 cross 2 matrix now and find out the uh, resulting saddle point in that strategies. And that will be the answer for us. So because in 2 cross 2, we really know it's easy to calculate for row player as well, the probabilities. So row player or column player, it doesn't matter to us. Like we can find out both ways. You can find for both in this case. Okay, then. So I guess this is the final answer, and yeah, this was what was expected in this problem. So now maybe we can move on to the next question then. So Okay, I just maybe want to check whether I have done this right. 2x plus 6 times 1 minus x. And this is 5 plus 5 is 2. And the third one is 7x plus 4 times 1 minus x. Because I think the answer which I have for this problem is a bit different from the answer which we have arrived at. So maybe I'll just see if we have done this correctly. Because I'm seeing the answer to it as written as 5, but I think the answer is incorrect. Like it should not be 5. It should really be this because if we choose the column probability as Z1 and Z2, row 1 will be something like 2Z1 plus 6Z2. So this is what we have actually plotted. Then second row will be 5. And the third row will be like 7x plus 4 times 1 minus 6. And so these really are the values which we want to see. And what we are doing is max. So since we are talking about the column player, the value will essentially be the max over the min. So basically row player will want to minimize, and while minimizing, row player will choose the lower curve. And now column player wants to maximize, so he'll choose this kind of a point. Okay. So I think this answer is correct. Maybe the answer I have written up is incorrect. Yeah. So this is the answer for us for this question. Okay, then. So maybe we can move on to the next question. So the next question states that it's an interesting question, at least, guys, um, from my side. So the question says, suppose the payoff matrix of a two-player zero-sum game is an antisymmetric matrix. A square matrix A is antisymmetric. So I hope everyone knows what a antisymmetric matrix is. So it's just that the AI comma jth entry. So basically the I comma jth entry of the matrix should be equal to negative of the j comma ith entry of the matrix. So like essentially what this means is that the matrix A plus A transpose should be equal to a zero matrix. So A plus A transpose should be equal to a zero matrix. So the problem asks us that the problem says that suppose payoff is an antisymmetric matrix. So payoff matrix A is let's say antisymmetric. Then there always exists a pure strategy straddle point. Saddle point. Is this true or false? So the question essentially asks us to like um, either prove that if a matrix is antisymmetric, then it will always have a pure strategy saddle point, or disprove it using an example. So maybe we should just look at some common examples which come to mind. Like what's a good example for uh, possible example? Maybe what are like uh, examples which we can for which we can check whether the matrix is like what are possible antisymmetric matrices and whether uh, they have a pure strategy saddle point or not. So maybe we just start off with the simplest. Maybe we can start off with the simplest of matrices, which is like a 2 cross 2 matrix. So let's say, uh, also note that for an antisymmetric matrix, the diagonal entries will always be zero because these entries should be negative of themselves, and it can only happen if all the things are zero. So yeah. And so let's say we have this as the basic diagonal. So 0, 1. So the 2 cross 2 matrix is just 0, 1. And like, since we really need like the age ij should be minus aj. So if this is 1, then this should be equal to minus 1. So let's see if this is an antisymmetric matrix or not. So, so Okay, so this is an antisymmetric matrix, but let's see if it has a pure strategy saddle point or not. So maybe let's just look at it from the perspective of like uh, calculating the V upper bar of A. So what I'm saying is let's find out the security strategy for the row player, and then we can come to the column player. So for the row player, what we want to calculate is like minimum over all rows, the maximum over all columns, and in terms of pure strategies. So note that if the row player chooses row one, uh, then the column player has the maximum set to one. So if the row player chooses row one, then then the column player will choose this one. If the row player has chosen the row two, then the column player will choose this zero because minus one is greater than less than zero. So because column player wants to maximize. So in one case, column player chooses one, and second case, column player chooses zero. Uh, and so since the row player really wants to minimize the value, so row player will say, okay, maybe this zero is the answer for us. So row player will say, okay, maybe this strategy, the row two is a good security strategy for me, and the like my security level is zero. But now so I'm doing it orally because I believe everyone should be comfortable with these pure strategy saddle points by now. We discussed these last time also. So now maybe we can look at the column player's perspective, the finding out the max min. So maximum over all columns, the minimum over all rows value. So note that maximum, so if the column player chooses column one, then row player wants to minimize the value. So row player will choose this minus one. And if the column player chooses column two, then the row player will choose this zero. And between this minus one and zero, the column player will now want to choose the maximum value. So column player again also chooses this zero. So in this case, it can be seen that uh, in this example, actually the column players and row players both have the same security level, which is this zero. So actually here there exists a pure strategy saddle point. So at least this from this it seems that at least for 2 cross 2 matrices, an antisymmetric matrix will have a pure strategy saddle point. But is this true for all possible matrices, all possible antisymmetric matrices? So actually this is not true, and maybe like you can extend this example also to see why is this the case. So actually, let's just say yeah, this is the matrix which we have. So this is minus one, this will be one, and this will be minus one. So let's say this is the matrix which we have right now. Actually, you can see that this is an antisymmetric matrix. And what I'm going to show is actually in this matrix, there will not exist a pure strategy saddle point. And why is this the case? Maybe let's just look at it from the perspective of the row player first. So we want to find out min max kind of a thing. So if row player chooses the row one, then the maximum here will be actually one. Column player will choose this one. Similarly, if the row player chooses row two, then again the maximum will be one. Similarly, if the row player chooses row three, then again the maximum will be one. So between these three, row player can choose any of these because all of these are ones. So row player security level is actually equal to one only. But note that for column player, again, what we can do is if column player chooses column player, we want to find out something like a maximum kind of a thing. So if column player chooses column one, row player will choose this minus one. In column two, it will again choose a minus one row player. And here also there is a minus one. So for column player, the security level will be a minus one. Whereas for row player, it was a plus one. So the security levels don't match, and hence there does not exist. So maybe I'll just write it. It can be seen in the above example that row player security level is equals to one, while column players security level is equals to -1. Hence, no pure strategy saddle point exists. So this statement is actually false, and yeah, this is an example. Consider the following anti matrix A. So this is the matrix, and this is the argument essentially. Okay, then. So I guess we have done this sixth question also. I think this sixth question was not too difficult, but I really like at least from intuitively one might think, okay, like the game is antisymmetric, so somehow one may be able to argue that there does not exist uh, like there exists a pure strategy saddle point, but actually there does not exist. Okay, then. So now we come to the the last two questions for the day, the seventh and eighth questions, which are really like a bit more involved than the a bit different than the questions already discussed, because the questions already discussed were more related to the lectures. But yeah, this question is uh, like not similar to the problems which were discussed in the lectures. Like it is related to the lectures, of course, but not similar to the problems discussed in the lectures. So there's this common data for question 7 and 8. The questions are quite small, but this processing this data is the main thing. So consider a game involving three players where every player has two pure strategies. So the game only involves like pure strategies. We are not talking about mixed strategies here. So three players and all of these players have like two pure strategies. So the total possible, let's say if we are talking about strategy profiles, then every player has two strategies and there are three players. So there are 2 raised to power 3, which are like something like 8 possible outcomes, not more than 8, because two pure strategies for each player means that total number of possible strategies are 2 times 2 times 2, which is just 8. So the player one strategies are player one chooses a row A or B, player two chooses a column C or D, and player three chooses a matrix M1 or M2 that represents players one's payoff as given below. So the first part is like a standard like maybe let's just say not a zero sum game. So we are talking about, let's say, a zero sum game here, and or even let's say not a zero sum game, but the problem is just essentially like the initial part is just okay, one is the row player, one is the column player. So player one is the row player, player two is the column player. But note that now there's a new twist, that there is another player who chooses the payoff matrix for the player one. So player one's payoff matrix is chosen by player three. So note that in zero sum games or whatever we discussed earlier, the payoff matrix was fixed. And then player one and player two were playing rows and columns and like finding out saddle points and everything. But now the problem has another layer to it, this problem, that there is additional player. So the payoff matrix is not fixed for us. So payoff matrix are there. There are two possible payoff matrices, M1 and M2. And this player three is essentially the player which will choose between these two matrices. Okay. So I hope the question is clear. Like at least not the question, but the setting which we are in. So like there's a row player, column player, but there is another player which I will refer to as the matrix player. So this is the matrix player, which chooses the matrix, the payoff matrix, which we'll be using. So now let's say now we have come into the domain of mixed strategy. So now assume that player one admits a mixed strategy of the form xa comma 1 minus xp. So what this means is player one plays the strategy A with probability X and plays the strategy B with probability 1 minus X. Similarly, player 2 plays the strategy C with probability Y and strategy D with probability 1 minus Y. And let's say the player 3 plays the strategy M1, basically chooses the matrix M1 with probability Z and chooses matrix M2 with probability 1 minus Z. And now so now the definitions of min, max, min, everything will change, right? Because everything which we had discussed in the lectures was with respect to two players only. So now they define us a new definition for min, max value of player one. So it's defined as a minimum over all yz, the maximum of x, u1 of x comma y comma z. So what this essentially means is so so u1 of x comma y comma z is essentially the payoff for the player one when x as a function of like, x, y, and z, like an expected payoff of player one as a function of x, y, and z. So what essentially you're doing is the the x player, the player which plays x, so basically player one will want to maximize this value. But the other players, let's say this is the min-max value which is defined for us. Like we are not talking about like why is this the definition, but let's assume this is given to us. That this is the definition that the player one will choose an x so as to maximize this value when we have fixed some y and z. So if y and z are fixed, then player one chooses an x such that this value is maximized. But note that these players y and z will choose their y and z in such a way that this whole value is minimized. And similarly, one can define the max min value. Okay, here also like sim after defining a min max value, one can also define a max min value, right? And like these are the strategy profiles, the mixed strategy profiles for the players, right? And now what we really want to find out is one question says we want to find out the min max value of the row player, and second question says to find out the max min value of the row player in mixed strategies. So now there's another level to the problem because now there's another player in the mix, which is the matrix player. So we'll have to start from the basics again. So let's see what are the basics when we are calculating the min-max values. Okay. So the min-max value is defined as minimum over y comma z, maximum of x, u1 comma x comma y comma z. So what this essentially means is that if some y and z are fixed, then row player will really want to maximize this kind of a value, right? So row player will want to choose a row such that this u1 x comma y comma z is really maximized. So note that okay. So note that if some y comma z are chosen, after that the row player will be choosing the x, right? So if y comma z are chosen in such a way, so okay, maybe what we should do is maybe we should be writing the uh, payoff for this uh, payoff for this row player in terms of y and z's. So let's say okay, row player for a fixed y comma z. Okay, so so for a fixed y and z, what we mean, what does it mean? So if so y is essentially the probability of choosing column C, and z is the probability of choosing out of one of M1 or M2, right? So what this essentially means is that hmm, like the matrix M1 is chosen with probability Z, right? So matrix M1 is chosen with probability Z, and then let's say uh, the column 1 is chosen. Okay, maybe okay, what we should be showing is so we need to find out the payoff for row player for a fixed y comma z. So what we'll be doing is uh let's say maybe we assume what I'm essentially trying to come to here is something like here what we did. So what we did is we found out the payoff for the row player on playing row 1, row 2, and row 3, right? And we'll be doing similar thing here also. So what we'll be doing is maybe I should just copy this and yeah, it will be easier for me to explain it then. So what we'll be doing is we'll be trying to find out the payoff for the row player when he plays row 1 or row 2. But now these payoffs will have both the term from y as well as z's. Okay, so what I mean here is yeah. So finding the payoff for the row player on playing row 1 in terms of y and z, maybe I should write in terms of y comma z. So if row player plays row 1, what will be the payoff for the row player? Maybe I should just do it here, right? Right. So let's say the row player plays row 1, but note that the matrix is not. So let's say the the matrix comes from M1. So basically with probability Z, the matrix M1 is chosen. And let's say the column C is chosen. So basically the value here is 0 and the probability with which this value comes is the matrix M1 is chosen and then the column C is chosen. And note that column C is chosen with probability Y, right? And now similarly, again, we say that, let's say, or maybe I should write it in a better manner so that it's easier for everyone to follow. So let's say I've chosen the matrix M1, right? So I have chosen the matrix M1 with probability Z. And now, like I'm talking about when the row player has chosen row 1 only. So with probability Z, the matrix M1 is chosen. And now with probability Y, the columns corresponding to the value 0 is chosen. And with probability 1 minus Y, the column corresponding to the value 1 is chosen, right? And similarly, what happens is with probability 1 minus Z, uh, should I some blanks here? It's fine like this. Yeah. Yeah. With probability 1 minus Z, the matrix M2 is chosen. And now really this this one is chosen with okay, maybe I should just put this here. And this column is chosen with probability Y and the payoff is 1. And similarly, this entry is chosen with probability 1 minus Y and payoff is again 1. Right? So this essentially like just becomes equal to 1, but it's not used to us. So this is when the row player is actually playing just row 1. If the row player decides to play row 2, what happens is again we'll have these kinds of entries, but just these values will change. So the first matrix chosen in priority Z, and if the first column is chosen in row 2, the payoffs become 1 comma 1. So this will become 1 and the second entry is still 1. And if the second matrix is chosen, the first payoff becomes a 1 and the second payoff becomes a 0. So this is essentially uh, the payoff for the row player on playing row 1, and this is the payoff for the row player on playing row 2. Maybe we should simplify these expressions a little if we can. So note that this just becomes equal to y times 0 is 0, and this just becomes 1 minus y. So the first term becomes z times 1 minus y, and the second term becomes this is y, and this is 1 minus y times 1. So y plus 1 minus y will just become a 1. So their sum is 1. And then this is multiplied by the 1 minus z. So this will be just plus 1 minus z. So this is the expression which will come to. And if you expand it further, this will become something like z minus zy. And the z and minus z will cancel out. So this will just remain like something like 1 minus zy or maybe 1 minus yz. is what remains in the end. Okay, I hope this makes sense to everyone. I've done a lot of calculations orally, but I don't think these calculations are hard anyways. So z minus zy. So plus 1 minus z. Yeah, so this is 1 minus yz, and what will this be equal to? So this will be equal to, so let's say this is again y times 1 minus y, so this will be equal to 1. So it will be z plus, this will be y plus 1 minus, so this term will be 0. So this will be 1 minus z times y. So this will be 1 minus z times y. Right? And now what is this equal to? This is equal to y minus yz. So this is really just equal to uh, y minus yz. So this will be just equal to uh, y plus z minus y times z. So if the row player plays row 1, then this is the value. And if the row player plays row 2, then this is the value. So, and this is as actually you can just write this as I think something like 1 minus 1 minus y, 1 minus z. So yeah. So this is the value 1 minus y times z, and like this y plus z minus yz can be actually written something like this. Like you can verify this by yourself also. That like this is not too hard to show. Just expand this out, and this will actually come out to be equal to this. So row one chorus. So if the row player plays row one, then he gets a value of 1 minus yz for a fixed yz, and he gets a value of 1 minus y times 1 minus z for uh, some other yz, right? And now what the row player really wants is to kind of maximize between these two entries, right? And so row player will choose essentially chooses row one when, so since the row player, so here what we want is min max value. So row player actually wants to maximize. So row player will choose row one uh, when this quantity is greater than this quantity. And when is this quantity greater than this quantity? Like when this is actually less than this. So like something like 1 minus y. So I'm skipping a bit of steps because we are being kind of out of time. So 1 minus y times 1 minus z is less than equal to y times z. So row player chooses row one when this kind of a thing happens. Maybe like this should be pretty good. Yeah. And chooses row two otherwise. So if we have something like this, that 1 minus y, and this is essentially equal to, so what does this imply? Yeah. So this is when the row player chooses row one, and this is essentially equivalent to saying 1 minus y times 1 minus z is greater than equal to yz. This is essentially equal to saying like you can just expand this out, and uh, you can just write it as like 1 minus y minus z plus yz, and like yz will cancel out, and this will essentially be equal to saying like 1 minus y minus z is greater than equal to 0. So this is what it will come down to. So whenever this happens, the row player will choose row one. Otherwise, the row player will uh, row 2 actually. So yeah, so this is just again equal to saying this y plus z is less than equal to 1. Y plus z is less than equal to 1. So if this kind of thing happens, then the row player chooses row 1, else the row player chooses row 2. Okay, so row player chooses row 1 when y plus z is less than equal to 1, right? So now we kind of have an idea of how will x play out. So we kind of have an idea of how is x going to play out that whenever whatever y z is chosen, if y plus z is less than equal to 1, row 1 will be chosen, else row 2 will be chosen. And now what they really want to do, what we really want to do in terms of yz is kind of minimize all of this, right? So what you want to minimize is so you want to choose your y comma z in such a manner that so what one wants is one should be choosing y and z in such a manner that if this condition is true, then like if y plus z is less than equal to 1, then this row will be chosen. So basically 1 minus yz expression, this should be minimized. And for minimizing this kind of thing should be maximized. Right now. So what I kind of mean here is something like this that uh, I'm talking a bit on a higher intuitive level because I think this will help us simplify the matters a bit. So we are choosing y and z. And if y plus z is less than equal to 1, then this value will be chosen, 1 minus y times z, right? And when will this value be, and what y and z want is essentially to minimize this value. So they want to make this value as small as possible. So what they want is to make this value as small as possible. And for making it as small as possible, you want to make this as large as possible. But y plus z is constrained to be less than equal to 1. So this will essentially be as large as possible when y plus z actually equals to 1. So now, so basically what this means is, uh, and you can actually see that like it's not too hard to see like using AMU inequalities and stuff. And this will be maximum when y and z both will be equal to half. Like if y plus z is equal to 1 and you want to maximize the value of y times z, it will be when y and z both are equal to half. Like you can verify this yourself. So y equal to z equal to half will be the, and note that at that value uh, like you can repeat same argument for row 2 also, and like for row 2 also you will see that same argument will suffice. Like you in this case you will want something like y plus z to be greater than equal to 1, but that will just essentially mean something like the same arguments can be used in that setting also. And like I don't want to get into that, but yeah, in that setting also you will see that y equal to z equal to half will be the uh, way to go. And this will be the uh, value at which this will be the distribution at which min max occurs. So actually and what will be the value equal to here now? So uh, when min max occurs like at y equal to z equal to half, this value will actually be equal to 1 minus half times half, which is 3 by 4. Is equals to 3 by 4. Like how did I arrive at this 3 by 4? You just put y equal to z equal to half here. And why was it that y equal to z equal to half was the distribution like using these arguments. Okay. So actually, yeah, uh, this was a bit of a different question because it involved different kind of arguments. But yeah, this is essentially the idea that like you first find out the payoff for the row player in terms of y and z, and you just now for this function you see that this like if the row one is chosen at that point of time, what are the constraints and when will these be constraint free maximized? And similarly, like you can repeat same argument for row two also, like for row two, what are the constraint when it is chosen and when will this thing be like kind of like when will this thing be maximized? And you will actually arrive at this thing that y equal to z equal to half will be the way to go. Like the values are designed in such a manner in the problem that this will occur. I'm not going to do this part also because we are running out of time and maybe we can discuss the eighth question now. Okay, so first we found try to find the min-max value of the row player in mixed strategies, and now the second question asks us to find the max-min value. And note that max-min value is again nothing but uh, in this question we have first chooses x and then has to minimize over this u1 values. So here essentially what's happening is so note that earlier what we did was uh, we we found out the payoff for the row players when he played row 1 and row 2 in terms of y and z. But now what we actually want is we want to find out the values for y and z in terms of x. So first an x is chosen and then y and z are chosen. And note that again, like we can treat the inner y and z as pure strategies because uh, the pure y and z's will be the ones uh, which will have the uh, biggest payoff, I believe. So, and what do I mean by this? Okay, maybe, maybe I guess we are running out of time for the session for today. So I guess I'll just, for this last problem, I'll just post the solution for like, I'll just type out the solution and maybe like I'll just post this solution also on the official docs page on the Google Drive of the course and like you can see the solution there. From there also, like I just write down the solution and you can just understand the solution when it is written up. And if there are any doubts in the solution, like you guys can ask me in the uh, next session. So next Monday, 6 to 8 p.m. Like if if there are doubts related to this question, like maybe you can ask those doubts also. But for now, I guess we should be closing the session since we are really like out of time and yeah, yeah. And this we can leave on as something which for which I'll just post the solutions directly. Okay, then. So I guess uh, these are the questions which I had to present for today. And like, yeah, these questions were like, I believe today's session was a bit more involved than all the previous sessions since it involved quite a bit of maths, but I hope everyone got the gist of it. And so, yeah, so I'll be closing the session for now and I'll hopefully see you guys next week in person and like, yeah, the same timing, 6 to 8 p.m. say. So thanks for watching the session, guys, and yeah, goodbye.